Hey all. Right, sorry I missed on this Monday. Just had a scheduled thing going on. No big deal. Nothing dangerous happening. All right. So if you wanted to watch this, that's why we have it. And we're busting into the section 3.1 and 3.2, kind of synonymous, and getting a couple parts. And hopefully looked at that. I believe we had an ed puzzle to get started on the chapter. All right, so this is not moving. Now it is. So we're starting with talking about graphs of exponentials, and this is the exponential slash logarithm chapter, and we're going to be doing the exponential part first. Think of this as y equals 2 to the x power. This little graph here. 2 to the 0 is 1. 2 to the first is 2. So that's 1 comma 2. Let's pretend that's a 2 there. 2 to the second is 4. 3, 4. And we could see why this graph will start taking off as I plug in big numbers. And then 2 to the negative first is 1/2. That's the negative exponent rule. 2 to the negative second is 1/4. And what will happen as you keep plugging in these negative numbers, the output will never be 0, but it'll be infinitely small. So what we do when we're annoyed by that, we draw in an asymptote to show that behavior. So there you go. And in this graph, let's flip it and call it y equals 1/2 raised to the x power. So that's when b is between 0 and 1. Well, of course, when you plug in 0 for x, you get 1 for y. That's why 0, 1 is like the most important point. You know that happens every time with an exponential function, unless it's shifted. But that's where you want to know that point's shifted. That's the point. This is the key point that we got to locate when we start shifting these graphs. Anywho, plug in 1 and you get a half. You plug in 2 and you get a fourth. And now that asymptotic behavior is starting to happen on this other side. You will never get to 0 no matter how big of an x value you plug in. On the other side, you plug in a -1 and it flips a half to 2. Input output, -2, 4. This is just exasperating. How many students don't understand this still? And I'm talking about students of the past as well. So there you go, horizontal asymptote, y equals 0, and feel free to read all this other stuff, all this good math stuff out of the book. Okay, so limits. Looking at that first graph, I'm doing this with these my sophomores, and they're doing just fine. As x goes to negative infinity, y actually approaches 0. It's approaching that asymptote as you plug in big negatives, but it's definitely going off to infinity there. And do understand that this is considered a growth function. As you read left to right, the graph goes up, so that is growth. Decay means it's going down when you read left to right. So when you plug in negative infinity for x here, you actually get infinity for y. You plug in infinity for x, it's actually approaching 0. So it's a decreasing situation. That's why it's called decay. So looking at these first couple, state whether the function is an exponential growth or exponential decay. Describe its end behavior using limits. I ain't got no time for this. I'm just going to do a couple of them. First of all, this b value is 1/4, and it's raised to the x. So A, it is exponential. Exponentials have to have x in the numerator. What? That is just the most ridiculous comment I just made. I'm frustrated with myself. X has to be in the exponent. The variable's in the exponent. So in a previous on that ed puzzle, y equals x squared. That ain't exponential. That's a quadratic. And so anyway, all of these are exponential. So this is an exponential decay. Exponential decay. And therefore, its end behavior limits will be this. Right? So that's what we're going to do. I don't care. I just want to get my movie over with. All right. And it's the point. We make the point there, and I think it's good enough. Y equals 8 to the x. Well, b is greater than 1. This sucker's really going to take off. It's going to be even steeper than this one. I plug in 1, I get 8. So this is exponential growth. So it would be that one. We'd end up with those limits. And let's analyze a couple more and just not worry about the limits at this point. Decay, growth. This is interesting. 0.25 is 1/4 raised to the negative x. And then actually, this is y equals 1/4 raised to the negative first raised to the x. Ooh, I'm doing some exponent rules here. This is all true, by the way. I could break this down into, a power raised to a power rule. Not really a big deal, but what I really wanted you to understand is 1/4 to the negative first is 4. So actually, in disguise, this is a growth exponentially. Now, with that being said, this is, in disguise, a decay. Negative exponent rule is all that I did there. Don't worry about my cough. I've coughed. I open up videos of 2013, and just talking irritates my chest sometimes, and it just happened throughout my whole career. So nothing going on here. Everyone just relax. All right. So review. This is a quadratic. So really, what we're going to do is we're going to take these exponential functions, y equals something raised to an x power, and then we're going to talk about all the transformations that could happen. So very similar situation here. This is a quadratic, though. This is a quadratic with a vertex of -3, -4. And then it's flipped over the x-axis and stretched by a factor of 2. Well, 0, 1 point is now going to be moved 3 left and 4 down. And then we're also going to vertically stretch this 2 to the power graph by a factor of 2 and flip it over the x-axis. So that's what we're looking at, and knowing those transformations when we look at these pictures. Now, it shouldn't be a huge amount of rocket science here, in order to figure this stuff out, because what you really want to know is, where does that 0, 1 point go? And it is 1, right? And I'm going to prove it. You plug in 1 for x, 1 minus 1 is 0. 2 to the 0 is 1. I plug in 2, I get 2. I plug in 3, I get 4. So this happens. And then I plug in 0. Well, I get -1. 2 to the negative first is a half. And then I plug in -1, that's 2 to the negative second. Okay, I get it. Now it's starting to get closer and closer here. So all that happened is it got shifted 1 to the right. That one ain't no big deal. Oh no. What does a negative on the inside of the exponent do? It actually does a y-axis reflection, because 2 to the x looks like this. I just graphed that one. Then if it's reflected over the y-axis, it's going to look like this. How could that happen, with this equation here? I just did it. 2 to the negative first is the same thing as 1/2. This is equal. You're like, wait, where'd that negative exponent go? You're killing me, Smalls. 2 to the negative first equals a half. So that's an identical graph. So boom, boom, boom. I usually only locate 3 points and then get the behavior that's going on with the graph and draw the asymptote. Whoa, don't cross that asymptote, Mr. Samuelish. All right, and then this is just a vertical stretch by 3. So watch what happens. I plug in 0 for x. 2 to the 0 is 1. But then 1 times 3 is 3. So it got vertically stretched there. I plug in -1 for x. I get a half. But a half times 3 is 3 halves. So all it does is stretch it out. But let's plug in -2 real quick and see that you still get close to 0 pretty quick. 2 to the negative second is 1/4. All right. And then, it makes me so sad how many students don't know what I'm doing here. This is 1/2 squared. This is 1/4. 1/4 times 3, though, is 3/4. So we're already less than 1. So we're still going to get this asymptotic behavior, because it doesn't matter how small of a fraction we have, times 3 is still going to be a very small fraction. So you still have this asymptote here. And then it gets ridiculous here. You plug in 1, you get 2, but 2 times 3 is 6. So there's the vertical stretching by a factor of 3, right? Could very easily be drawn by input, say it, output, blah, 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 Mr. Samuelus. And then what's f of x equals 3 to the x compared to 3 to the x plus 4? Well, plus 4 actually moves us up 4. 1, 2, 3, 4. And you know what really gets moved up 4 is the asymptote. It's very simple to do this. Plug in 0 for x, 3 to the 0 is 1. 1 plus 4 is 5. That's where the 0, 1 point ended up. That's what I told you. Like in a parabola, you want to know where the vertex ends up with these shifts. For here, you want to know where the 0, 1 coordinate ends up, and then you'll know where the asymptote is. Okay, so hope you remember this, blah, blah, blah. 3 to the first is 3, plus 4 is 7. So we're still getting at that behavior. Oh, I just crossed the asymptote. I should have like a buzzer. And then 3 to the, you got to pull out a -1, and then it's x minus 5. So this actually goes 5 to the left, and it is a y-axis reflection. So, or you can think of 3 to the negative first again as 1/3. So where does 0, 1 end up? It ends up 5 to the right, and I'll prove it, and you probably want to prove it by plugging in points. Okay, so it's saying if I plug in 5, I get 1. 5 minus 5 is 0, times -1 is still 0. 3 to the 0 is 1. Booyah. All right, what happens when I plug in 6? Well, here's the problem. 6 minus 5 is 1, but then it's negative. 3 to the negative is 1/3. So, come on. Right? And then that goes there. 4 minus 5 is -1, but then -1 is +1. So you end up with 3. So your life is so much easy if you just learn how to plug in points. Why is he yelling? Just, I don't know. Oh, it's so hard. No, it isn't. Just know how to, plug in points and do stuff. Okay, crabby on a Friday. Yeah, I'm making this on Friday. Yeah. Okay, so I guess we're done with the graphing here, but we won't be. I'll keep bringing up graphing. Especially when we do logarithms. To graph logarithms, you got to know how to graph exponential functions. Okay, continuing on with the fun. Okay, so we were kind of like struggling. What do we want to show you on this? And it does kind of come out of left field. So first, we just talked about graphing. All right, so that's how you graph functions. And the worst they could be is like with all these transformations. And we'll probably just keep it to right-left shifts, um, up-down shifts, flipping over the x-axis, flipping over the y-axis. Not a big fan of the dilations by a factor of 3 because a lot of people want to make that 3 times 2, which is 6. And that's not what happens at all. You got to do your order of operations for input output on that. But then when you get a word problem, this is now not the graphing section. This is like section part 2. Whenever it says something is exponential in nature, then by default, you will write this equation down. Now you're going to say, wait a minute, that does not have what we have down here. And I forget what they have in the book here. I guess I really don't care. Y maybe equals A times B raised to the T. A equals the initial value of this situation. And then B represents, what is this function doing? Is it growing or decaying? Okay, so B ends up equaling, well, I'm actually going to go into leak into 3.2 because I think that's really the smartest thing. 1 plus R. So if B is greater than 1, then it's going to be a growth because when you multiply things by numbers greater than 1, they go up. All right. And then B is less than 1. I hope you saw my face there because that was kind of common sense. When B is less than 1, and if you multiply things by numbers less than 1, they go down, and that is decay. So you're saying this doesn't show that? Well, it does. P of t is y, and what P of t stands for is population over time equals P sub 0, initial population, times B raised to the t. And B is that, rate of growth situation going on there. Sorry, voice is irritated. So you know what you do? You trick yourself. You make this year 0, and therefore this makes this year 10. And these are coordinates. I have no time. So what this represents then is the initial population right here, since I call this year 0, since it's the starting point of when we started looking at this. So P of T equals, in San Jose's model, 782,248 times B raised to the T. And then I have some other unknowns. I have B, I have T, and I have P of T. But then when I look at this, I can take this second coordinate and start plugging it in. And this would go here. And then what we could do is see what is the average rate of growth over these 10 years exponentially, because populations usually do grow exponentially. And then what you'll find is you have 193, 782. So again, hopefully you know why we called this the initial population. Because it's at year 0. We cheated. I didn't cheat. We just made it up. Hey, we're looking at the data starting in 90 on. So year 90 is year 0. That's our initial population. Or if I plugged in 0 for T, P, B to the 0 is 1. Then that's what P of T is after 0 years. So either way, P of 0 is the initial population at year 0, 1990. And then hopefully you understand what you would do in order to solve for this. B to the 10th equals 895, oh boy, 193 divided by, am I doing this right? Divide both sides by 782. And you should know that this is growth. I mean, look, the population went up over years. Now, like Illinois' population, that's going to be plummeting because our politicians are a bunch of crooks and they steal all our money through taxes. And then when they find out they haven't stolen enough, they raise them. Mr. Samuels is getting ready to leave. Can't afford it, man. We keep electing them. Okay, so how would I solve for this? I'm getting ready. And the answer is yeah. And I was typing on my calculator. Sorry, I'm not showing it on the screen. You square. No, you 10th root this. Oh, fine. I got to show it on the calculator. This son of a nutcracker. I just know it's going to take forever. You know what? Forget that. You can see my screen. You see that? Okay. And then I'm going to hit square root answer. Watch, I'm going to get rid of that calculator. You take too long. You frustrate me. Go away. Okay. Hurry, just, yeah. Okay, where's the camera? See that? So I did the blank divided by blank, and then I did it wrong anyway. Clear. I got to find the 10th root button, which is math, and then it's the X root button. But I actually have to hit 10 first. I don't think this is any faster. This is awful. There we go. So it's the 10th root. I hit 10 first, then I hit the root button. And if the X still stays there, that's fine. You have an older calculator. It's all good. Answer, right? And then that is 1.01357. So that's what the B value is. So here's the model for this San Jose. Population over time of San Jose equals the initial population forced in the question because we called that year 0 times 1 point. Boy, for populations like this, you probably want to take this out. Don't worry about like, what are the rules? What should I take it out to? 0136, let's say. I rounded 57 to 36. All right. T. That means that this population is going up 0.0136 or 1.36% per year, right? Because this is in years, per year. And then that kind of goes along with what we have below here. And that's why I kind of brought in the B equaling 1 plus or minus some R value. In this case, it's a plus because it's greater than 1. That's what all this garbage says here. So I'm jumping right to this. Well, there's San Jose. Is that what? What the? That's what I just got for that answer. Oh, they got it right here. Oh, geez. Well, I just said it then. So growth and decay rates. When you're looking at example 5, you have to tell me, is this a growth or decay? We just did this one. This is a growth by a factor of 1.36%. It's not a that's a G. It's not a All right, this one's a little tougher. This is less than 1. When I multiply this by Detroit, everyone's leaving Detroit. Should put Illinois in here somewhere. Yeah, that number would probably be even lower. 0.9858. Multiplying that by that makes that number go lower. So this is a decay. Now, what's the decay rate? You actually have to do, you can do 1 minus and then just say it's a decay rate. It is like a negative thing, but I guess I have to do this on the calculator too. 1 minus 0.9858, 0.0142. So 0.0142 happens there. That means it's a decay rate of 1.42%. Now, if you want to slap a negative on it, fine, but you're using the word decay on it, so I think you're fine. Okay, so determining exponential functions with given values, then we could do a half-life question and then another one about doubling. Determine the exponential function with the initial value of 12, increasing at a rate of 8%. I'm just going to put y. Y equals initial value a times b isn't 8, it's not 0.8. B is 1 plus or minus r, depending if r is a growth or decay. R is 0.08. Oh, I get so sad with students that can't deal with percentages. If you make 8%, 0.8, that's 80%. That's ridiculous. Okay, can't teach grade school, although I just did. So that is that model that represents that. Let's move on. Ooh, bacteria in a petri dish. Or is it Petri? I don't know. Okay, suppose a culture of 100 bacteria is put in a petri dish and the culture doubles. So my quick question is what's the rate of growth if your money doubles, if bacteria doubles? And I bet you people are going to say like 200% is your rate of return. Incorrect. Your rate of return is 100% if you double your money. You're getting 100% of your money back. So remember, B equals 1 plus R. R is not 100. It's 100% turned into a usable decimal, which is 1. So the B value ends up being 2. So sure, the B turns into 2. The rate of growth is 100%, which is 1 as an R value. So anyway, y equals a times b raised to the t. In a doubling, sure, this turns into 2. Suppose a culture of 100 bacteria. Predict when it will be 350,000. Now, I wish we wouldn't have done this now. If I would have thought about it back in our CAT meeting, I would have said, you know what, let's save this question for after we do logarithms. But since we don't know what logarithms are, this is what we have to do. We have to put this and go to our graphing calculator and put this in our Y1 screen, put this in our Y2 screen, and find the intersection between these two graphs. Notice the scale. I mean, goodness gracious, this is y equals 350,000. So our y maximum must be pretty large. It must be like at least 400,000. And then how long is it going to take in hours for it to happen? That's a guess and check. I probably would have put 20 on my x maximum. And then you would have seen the exponential growth and then seen the intersection, and then you hit the intersection feature on your calculator. Okay, so hopefully that makes sense. I know we're going over this fast. It's a YouTube video. You can stop and make it happen here. And then you can read this on your own. Half-life. Oh man, there's a whole bunch of half-life. I love half-life questions. It's how we know so much about our universe and our Earth and how old the universe is and blah, blah, blah. It's fascinating. So many different half-life scenarios. Carbon-14. That's if good dear old Mr. Samulus dies and they bury his bones, and then in like 4,000 years they find his bones as if they cared. They could analyze the carbon left in my bone and find out that it was 4,000 years ago that I was buried. Why are we talking about my burial? So half-life means you're losing half of the material. It's very simple. So as soon as you hear half-life, R equals, I don't know why, negative a half, or you're losing 50%. So that means B equals 1 minus a half, which is half. So in a half-life question, B is a half. How many times do I have to say half? It's very simple, and you have to have this memorized. Okay, but here's the other problem. This is a little trick. Okay, the half-life of the substance is 20 days. All right, that affects the exponent. The exponent is in time, but this is in 20 days. I don't have time for this. We're just going to have to get this. The exponent is x over 20. Here's why. Think about when I plug in 20 for x. 20 divided by 20 is 1. Half to the first is half. I will be able to take half of something at that point. So, and there is 5 grams initially present. So here's 5. So let's think about that again. In 20 days, 20 divided by 20 is 1. Half to the first is half. Half of 5 is 2.5. In 20 days, there should have been 2.5 grams left by the definition of what half-life means. Find a time when there will be 1 gram remaining. That's where the 1 goes over here. All right, so this is the biggest thing. Always, whatever the half-life time is, it's x over that half-life time in the exponent there. Alrighty then. Is that it? Oh, this is amazing. All right, sorry I missed Monday, everybody. At least this melodious video makes up for that miss, I hope.